Okay, so I'm going to work through a bunch of different problems. First thing I want to look at is these multi-loop circuits. So let's look at this as a Spring 18 exam number 3 and number 3. Exam number 3 from Spring 18. So let's first consider the circuit. Which of these equations is correct? So when you have this type of problem, and you will, you just look at the first number and then ask, okay, what element I'm dealing with, and obviously I'm dealing with this 3-volt battery, and since it's positive, I know that I'm going in this direction. Now remember, with these you have a couple of directions to consider. Well, for the batteries, you really just have to think about the traveling direction. And so if I'm going in this direction, that means I'm dropping in energy, so my change in potential is negative V. If I'm going in this direction from low to high potential, I'm increasing in energy, so I have a positive V. So in order to get a plus 3 volts, I have to be going in this direction. All right, so I go along, I have plus 3. My next element should be minus 2I1. Oop, I do. I come here, I look, I have a plus 5, so that's in that direction, and then minus 6I1. Now this term is incorrect for two reasons. First, it should be positive, and it should be 6, and then it should be I2. So both the sign and the current are wrong. Now let's look at the next one. I have 5, positive 5, so I know that I'm going in this direction from low to high. Minus 6I2. Whoop, I already have an issue there. That should be plus 6I2. And then minus 6, that's correct. I'm dropping. So everything but the sign on that 6I2 is correct. Let's look at the third option. I have minus 6 plus 2I1. So that means I'm going in this direction from the 6-volt battery. Minus 2I1. Excuse me, plus 2I1. That's correct because my current is going in this direction. I'm going in the opposite direction, so I would have a plus 2, which is my resistance, times I1. So that is correct. Minus 3, I'm dropping in potential. Whoop. So that is right. C is the right answer. Let's go ahead and just look at the others. My I2 plus I3 equals I1. I just want to pick a junction. I have I1 going out, I2 going out, and I3 going in. So I3 is equal to I2 plus I1. Oh, that's not what it says. It says I2 plus I3 is equal to I1. So D is not right. And now finally, that last part, 3 minus 2I1, 3, positive 3. Minus 2I1. That's correct because I'm going with the current through the resistor, so it should have a negative potential drop. Plus 6I3 equals 0. Okay. Now, you might think it would be 6I3, but this is a battery, so I shouldn't really have that I3 there at all. That's what I would do to make that correct. So you will have a question like that, absolutely, on your exam. By the way, your exam will not have free response, almost certainly, unless we come up with some other solution, but almost certainly no free response. So it'll look more like this. Now, number 4, if I2 is 0.17 amps, so I have 0.17 amps right here to the left, so it's in the correct direction as it's drawn. What is the magnitude of I3? That's a little bit tricky because you might say, well, I should just use the bottom loop. If I use the bottom loop, let's just write the equation for that. I'm going to start here and go in this direction. So I get 5 plus 6I2 minus 6 equals to 0. Well, that doesn't really help me to find I3 at all because there's no occurrence of I3 in that equation. If I write the big loop, there's no occurrence of I3 in that equation either. No, what I have to do is I have to write the loop or the junction rule. We did this earlier. What was it? I3 equals I1 plus I2. So now I know what I 2 is, it's 0.17. So if I can just figure out what I1 is, then I'll know the answer. So I can pick either, to find I1, I can use either the top loop or I can use the big loop. Let's use the top loop. So I'm going to start here and go in that direction. I'm going to go in the same direction as I2. So that's going to be minus 6 I2 minus 5 plus 2 I1 minus 3 equals 0. And then I would solve this for I1. Minus 6 times 0.17 minus 5 plus 2I1 plus 3, excuse me, it should be minus 3 equals to 0. I'll leave you to solve that for I1. But once you find I1, to find I3, you just take the sum of those two, and then that will be your I3. By the way, if I1 works out, well, let's just go and do it. So minus 6 times 1.17. That's equal to 1.02 minus 1.02 minus 5 minus 3 equals negative 2 I1. And so I'll just round that off to 1. It's minus 9 divided. So I1 equals 4.5. And so to find I3, it's going to be 4.5 plus 0.17. So it should be 4.7 would be the answer. All right, expect some multi-loop circuits. Let's do this number 5 as well. Some of you asked about multi-loop circuits, and then we'll get into the right-hand rule stuff. So here I want to know the current through the 3 ohm resistor. I don't give you directions for the currents here, so you just have to pick some directions. I'm just going to pick them all going down, and I'll call this I1, I2, and this will be I3. Doesn't matter what direction you pick. Doesn't matter at all. So I've just picked them down for no reason. It's not going to make it easier or harder. And then I need to figure out, well, which equation can I write in order to find this. Now notice, look, if I write the equation for the left loop over here, if I write the equation for this loop, then I'm going to have a formula that has 3I1 and then also 2I2 as I write that loop rule. There is an easier way. I'm going to instead write the formula for the big loop. So let's start here and go in this direction. So I'll have 4 minus 3I1 minus 12 equals to 0. So that is minus 3I1 equals 8. So I1 is equal to 8 over negative 3, just 2.7. And notice that since it came up negative, I didn't ask you for a direction, but since it came up negative, I know that I chose this direction for I1. So I1 should be 2.7 amps upward. Because I chose that direction incorrectly, that comes out since the current came out negative. Okay, let's see here. Number 8, wanted to look at. Okay, so after 3 time constants, after 3 tau, what percentage of the final voltage is on an initially uncharged capacitor charged through a resistance R? So we want to look back at our equation sheet. And let's see, I'm looking for the charging capacitor. If you look on your charge for a charging capacitor, it looks like this. Now that should that should make sense to you, because if I think about Q over T for a charging capacitor, it's going to look like that, because the charge will increase for a charging capacitor. And I know that this function right here, this 1 minus the exponential, will give me that kind of shape graph. Whereas this function, which gives Q for a discharging capacitor, will look like this, which has a, or excuse me, not like, yeah, well, it will look like that. So, I can then say, well, Q is equal to big Q times 1 minus e to the minus t over RC, which is tau. And I want to know what percentage of that final voltage is on an initially uncharged capacitor. Well, Q is equal to CV, so I can just say that V is equal to V naught times 1 minus e to the minus t over RC. Those things are just interchangeable. In fact, I think that equation is over here, is it not? Yeah, see, here it is right here. So I have my voltage as well. But I know that Q and V are directly proportional. And I'm looking for V over V naught. I'm looking for a percentage. That's 1 minus e to the minus 3 tau over tau at 3 time constants. Then these two taus cancel out. And I just really want to know what is 1 minus e to the minus 3. 1 minus, e is just a number. It should be second natural log on your calculator to the negative 3. When I do that, I get 0.95. 0.95 or 95%. So after 3 time constants, your capacitor is 95% charged. After 10 time constants, we'll assume that it's fully charged, so it's basically 100% charged. I just want you to know how to deal with exponential functions in this. The RC circuits are important, but more important, I want you to know how to deal with these exponential functions. I don't even want you to memorize the equations. I just want you to have some feel for what the functions are like. They're very important in science, in the physical and biological sciences. What was that, number 8? Number 14. Positive charge is traveling towards a wire as shown. The charge follows a path as shown. What is the direction of the current in the wire? So, you're very likely to have a question like this, and it's a two-part question that uses 2 different applications of the right-hand rule, neither of which is an easy application. The first thing that you want to do is just to think about this situation. Forget about the wire for now. I have a positive charge traveling with a velocity in this direction, and it experiences a force in that direction. That force is what causes it to move over in that direction. So I let my index finger go in the direction of V, my thumb goes in the direction of F, and that means that the magnetic field, in this case, is out of the page. So B is out of the page. Index finger in the direction of V, thumb in the direction of F, and so the magnetic field, which is my middle finger, points out of the page in the plus Z direction. So that's the first part. And by the way, I posted another video of just the right-hand rule of, it was me in the video, so you can practice that with the right-hand rule, and that's how you do that. Now the second part of this is I imagine a wire with a magnetic field that is out of the page on this side and into the page on that side. And I want to know what is the direction of the current. Well, the direction of the current is either left or right, because the current is going to be constrained by the wire. And I want to know, does a left current give me an out of the page on the top? Well, I can just try it out. Let my thumb point to the left. My fingers would wrap around in the top, going into the page, and then out of the page. So it's not to the left. Imagine if it's to the right, the current, my thumb points in the direction of the current to the right, fingers go into the page on the bottom and out of the page on the top. You try it, okay? Thumb in the direction of the current, fingers go into the page on the bottom and out of the page on the top. So that is the answer. What is that? To the right. Going to see some questions like that, okay? There are lots of different ways to ask that question, so don't try to memorize the different situations. Just learn the right-hand rule, the 3 different applications, and those are 2 of the applications. The second application is basically the same as this one. As I said, that's in that video that I posted earlier. What was that, number 14? Number 15 as well. Okay, you're going to see one of these too. This is like a mass spectrometer. I think y'all use mass specs. Well, you chem majors, of course, will in your instrumental course, but I think maybe in organic you get into some mass spectrometry. Anyway, it's a very important technique that allows you to find the mass-to-charge ratio of an unknown particle. So scientists use it from all different fields to determine what type of materials they're dealing with. And so these are sort of the basic fundamentals of it. A positive particle travels as shown through the magnetic field. In order for the particle to go through undeflected, an electric field must also be present. What is the direction of that electric field? First of all, let's just figure out what is the direction of the magnetic force. So there's going to be 2 forces, the magnetic and the electric force. But the magnetic force is I have my finger in the direction of V, my index finger. My middle finger points in the direction of B, that's into the page. So my magnetic force is going to be upward like that. That means that my electric force, in order for this thing to travel through undeflected, my electric force has to be down. Now, what direction must the electric field be in order for the force on a positive particle to be downward? Our electric field is going to be down. A positive particle will travel in the direction, or feel a force in the direction of the electric field. If this was a negative particle, it would be different. I'll work it for a negative particle, but for the answer for this one is down. Let's try it for a negative particle. I'm going to erase everything here because it changes lots of the answers. If I have a negative particle, so say not a positive particle, but I have a negative particle, I do my right-hand rule just like I did before. V is to the right, magnetic field is into the page, and so that means that my force, my magnetic force, would be up like we had before, but because it's a negative particle, my magnetic force is actually down. So my electric force has to be up. Now, what is the direction of the electric field in order for a negative particle to move up? Turns out that the electric field has to be down because a negative particle will move opposite the direction of the electric field. It's sort of like the negative particle moving uphill that we talked about, that it will move opposite the electric field because, you know, it's a negative particle. They just sort of do wonky things. Remember that if you have a question that says negative particle, and as soon as you read negative, you circle it and say, oh, I better come back at the end and switch the direction of my answer, because some of you are going to have issues with that if I give you a negative particle, that you have to switch the direction of the answer. Let's do spring 19 on number 10. Okay, this one's similar to what we were doing before, and this is a great problem because I said it combines 2 different right-hand rules. So let's try it out, and then we'll do some other right-hand rules. Let's see how long we are, and I could stay here for hours. So, as I said, we first start with this part of the problem. I have a velocity, a positive charge moving with a velocity in that direction. The force is in this direction. So I want to know what is the direction of the magnetic field. I let my index finger go in the direction of V. My thumb is, you try this, index finger in the direction of V. My thumb goes in the direction of F, and so that leaves my middle finger pointing into the page. So my magnetic field on this side is into the page. That means my magnetic field on this side is out of the page. The current that causes that sort of magnetic field has to be to the right. Try it. Thumb pointing to the right, the fingers go in on the bottom and come out on the top of the wire. Let's just sort of peruse some of these other right-hand rule questions and see any others that you might have. Okay, this is another application. What is the direction of the force on the wire? This is F equals ILB. So we let our index finger go in the direction of I. Our middle finger goes in the direction of B, which is into the page. And my thumb, which now points to the left, is our force. I want you to recognize that I could have whittled the answers down to just two options because I have a y-axis taken up here, a z-axis taken up here, so I know that this has to be in either the plus or minus x direction. So I can get rid of the y answers and the z answers. It has to be either to the left or the right, but it is to the right. Number 11 is a little bit different. So here I want to know what is the charge of the particle. Let's just assume that it's a positive particle, and I have V in this direction. My force is in this direction, so V is to the right. Point your index finger to the right. You might look a little goofy, but point your index finger to the right. Let your thumb point upward, and then your finger goes into the page. So if this was a positive particle, it would have a magnetic field into the page to cause it to take this path. That tells us then that this has to be a negative particle because it's doing the opposite of what you would expect. Let's, number 4 is one like you might have. I have a capacitor that's fully charged by the battery, and then the battery is removed, and the capacitor is allowed to discharge. Okay, so first of all, which equation am I going to use? Am I going to use the one that gives me this kind of function? That would be the 1 minus e to the minus t over RC equation, or am I going to use the one that looks like this? That's the e to the minus t over RC, right? This thing right here approaches 0 as t gets really big. Well, this is a discharging capacitor, so I'm going to use this function in that equation. You can look it up. Q on a discharging capacitor is equal to Q e to the minus t over RC. And I'm looking for the charge 10 seconds after the capacitor has begun discharging. I know that 10 seconds is just twice the time constant. Tau is equal to RC. That's 2 times 2.5. or 5 seconds. So I know that it's not fully discharged. I can get rid of that right away. It's only not even, I don't know, more than halfway discharged, but not really close to being discharged. And so I just have to calculate it. This is going to be equal to C times V, e to the minus t divided by RC. By the way, just a little hint, I almost always give you mega ohms here and microfarads here just because it makes your time constant a nice round number. You don't have to have any metric prefixes. The mega and the micro cancel out, and that's the way it'll be on your test. That's not uncommon actually in RC circuits because you're often wanting, you know, like a real life kind of time constant because these RC circuits are used for timing things like flashing lights, which flash like every second. And so they'd have an RC circuit with a time constant of approximately a second. Other timing circuits, you're going to want similar time constants. So C is 2.5 times 12, 24 plus 6. That's 30, right? 30, 2.5 times 12, 24 plus 6, yeah, 30 times e to the minus t minus 10 divided by 5. Try this on your calculator, because if you've never done it, you might not know where the e is, and you might actually do a button that looks sort of like the exponential function that's not really the exponential function. So just try it out, please, right now. And I get 4.1, 4.06, or 4.1 microcoulombs. So B is the right answer, and that sort of jives with what I think. Because look, actually, none of these others really could be reasonable. It can't be 60. That means that it's actually gaining charge because it starts with 30 microcoulombs. And likewise for C and E. So really B is the only reasonable answer. All right, we'll do one more. Number 7. Actually, I want you to look at number 6 and 7 because I want to show you the equations for these, which are really, really similar. And I don't want you to be confused by them because often students are, but I don't want that to be you. So on my equation sheet, I have 2 equations that give me magnetic field. I have this one, B equal mu naught I over 2 pi r, and then I have this one, B equal N mu naught I over 2r. Let's look back at the thing. So this is B equals mu naught I over 2 pi r. And this one is B equals N mu naught I over 2r. I can tell the difference in these because they're really similar, but this one has N in it. N is the number of turns. And so I'm looking for here the value for N. Anytime I'm talking about a cylinder with wires wrapped around it, that creates an electromagnet. It's a solenoid. That's the solenoid switch with the cool British guy. That's going to be that equation. I can always tell because it has that N in it. And this equation, on the other hand, doesn't have N in the equation. So I can try this out. Here I'm looking for how far. So I'm looking for R. R is going to be equal to mu naught I over 2 pi B. That's 8.85 times 10 to the minus 12. Times I, which is 0.5 amps over 2 pi, and then B was 0.02 Tesla. One of our alumni drives a Tesla. I want a Tesla. Actually, no, I don't want a Tesla. I already drive enough to have a Tesla. But anyway, she has a Tesla, and it's really nice. Anyway, you can figure out what that is. I don't know what the answer is, but you can figure that out. Just put that in your calculator. Please try that on your own, okay, so that you make sure you're getting all the numbers right. And then here, I'm looking for the number of times that I have to turn this wire, because this is where I have this coil of wire, and then that, when I put a current through it, it generates a magnetic field. So N is equal to B2R over mu naught I. B is 0.02. 2. R is 0.5 meters over mu naught I. .5 amps. And so then you can calculate the number of turns required for that. Okay, let's see if there are any others I want to look at. That I've gotten most of these. Make sure that you're up on your home circuits too. You need to know the 3 different safety features. The GFCI, which turns off when your current in exceeds the current out. Because if you have a difference in those 2 currents, that's bad. That means that you've like dropped your hairdryer in your bathtub. Who uses their hairdryer in their bathtub anyway? But that always seems to be an issue in television. The circuit breaker, which turns off if your total current exceeds some maximum current. And then also, the grounding. So the grounding is that 3rd prong, and in your house, there's a wire outside that goes to the ground. Well, shoot, let me just redraw it over here. There's a wire that goes down into the ground, and the 3rd prong is a direct path to that wire. It's a clear path to the ground outside of your house, so that if electricity is loose, like if it's not where it's supposed to be, instead of going through you, it will go to that ground. That's all for now. We'll have another help session some point later. If you have any questions, just please email me.